Hello, this is Robert Guderian, and today we are looking at even more randomness. That is the topic of the week, and we already talked a little bit about shaping experiments last lecture, and we're going to get into that a little bit more. And we're going to talk about the scientific method, and my boiled down version of the scientific method that I'm going to use here is 4 steps. Arguably, there's 7 or 9, depending on the model you choose to follow. This is the smallest version you could have, where you have a hypothesis, which is basically an informed idea that something's going to happen. You're going to make predictions, saying, at this point, I think this is going to happen. You're going to test those with multiple trials, not just one, because that's not actually helpful. And then you're going to do some analysis. And then if we're actually doing full science, we'd be publishing it and repeating those trials again in other places to make sure that they are valid. And that repetition piece is very easy for us. We don't have to mix chemicals. We don't have to put chimpanzees into a room and then murder them afterwards. All we have to do is write a loop. No chimpanzees were harmed in the making of this lecture. But we do need some data to process. And that is, of course, where this randomness comes in. You saw this last time already, where we designed a bit of an experiment and tried it out. And that experiment went on for longer than I expected, but was really good, and I enjoyed it. So what is our hypothesis? Our null hypothesis is always that nothing happens. That our experiment was a failure. Our hypothesis 1 is our first potential outcome. We think that this is going to happen. And we're going to have a second hypothesis. Well, if it's not that, it could be this. And we're going to have any number of hypotheses. That's fine, as long as they're actually informed. So let's talk a little bit about dice. I've talked about dice probably in my class. That's why I say back to dice. Let's compare a D20 and a D10, or a D12. If you like geometric shapes, these, of course, there it is, are quite beautiful. Here's your D12. And you want to roll these. And at some point, if you have a D12 plus something, it will consistently beat the D20. What number is that? Well, the average number rolled on a D12 is 6. And the average number rolled on a D20 is 10. So 6 plus 4 is 10. So my hypothesis 1 would be that we'll beat the D20 sometimes if we have plus 4, and we can beat it reliably with a plus 5. So that would be my hypothesis 2. And those hypotheses are not mutually exclusive, right? I have 2 different pieces of information I want to put into my system, and I want to be able to simulate both. But so there you go. We've made a prediction. We've made hypotheses. What are our tests? Well, we do need to store these results. I'm going to store them in an array because that is fine. You could arguably make a dictionary. I don't think it's the right tool for this job because there's no sense of keys. Your key would be like experiment number. If you're doing lots of experiments, you could have D12.5 or plus 5 as your string for your dictionary to show you all of these repeated trials. But that's taking a step back where you have already done D12 plus 1, D12 plus 2, D12 plus 3. And that is larger. So we have lots of repeated code. How can we design our methods to write the least possible? So we want to write the method names and when they return, and we want to tell this story. That goes back to week 0. Part of that reading was, in order to write a program, you need a computer and you need to have a story you're trying to tell. And this story that I'm trying to tell you is that D12s can beat D20s. But it needs to have some kind of modifier to help it out. And importantly to this week, we want the same rolls. We need to do apples to apples. I could write a single program that would add all these modifiers and do all these things. But I'm going to write one program that I'm going to run many times. And I want to write abstract code so it'll always work. So that's important to me. So my story will be, I need a function to roll a die and add a modifier. I'm going to have n repeated trials, and I'm going to set a seed so that my dice rolls are always in the same order. And then I'm going to collect all those results and display them. How do I want to do that? That is part of my story because I need that for my analysis. I could store that in a dictionary, or I could store it in, if I know that I'm only going to run 5 experiments, maybe 5 variables is okay. I could be very fancy and say that I'm keeping it in a list, and at spot 0, this is actually +0, and at spot 1, this is spot +1. Oh, that is 1. And spot 2, it's going to be +2. I could be clever like that. I think that is compelling, but it's not actually helpful. Maybe storing in a dictionary would be the best in this case. So let's do this. If you're not interested in the example, all the rest is an example. There's a meme at the end. You can just forward to that. The rest is me just programming this up. So for the people who don't like the example, farewell. For everyone else, buckle up. Let's have some fun. Program. Okay, def. All right, let's import random first. I am not going to set my seed right away. What I want out of this, I want to be able to do repeated trials right away, and I'm going to set the seed at the beginning of my trial. And that way, I will always have the same seed. I need a cool number. I've kind of already oversold 42, but whatever. It's a great one. Def, dice roll. And I want sides, and I want a modifier. My dice roll is return random.randint from 1 to the number of sides, and that's up to and including, which is really quite nice in this case. And I want to add my modifier. So that is good. That's it. 1d12 plus something sides would be 12, and then we get our modifier, and we're happy. Cool. Now I want to be able to roll this many times. And def battle. Dice 1 sides. Dice. Or it is die, isn't it? Somebody out there is going to be dying. A single dice is actually a die. 2 dice. Dice is plural. It's like data. Die 2 sides. And I can make this super general and say die 1 modifier. In my story, I actually didn't talk about that. I could actually add things to my D22. I need not use that feature, but I can put it in, and that's okay. If you look at Martin Fowler, he would be like, no, don't do that. In this case, I think that it's easy enough to add this general code that it's okay. So from this function, what do we want to return? So let's write a doc string. And this will actually help us program. Oh, wow, it actually tells me all my modifiers. That's so cool. Compare 2 dice. This would be dice. Return true if die 2 beats die 1. What do we do on a tie then? This is where science comes in. You actually have to ask yourself, this is an edge case where these two problems meet. What do you want to do? What are you trying to set out to prove? Well, I wanted to say where the D12 plus something beats the D20. I don't care about matches. I want to say beats. So I'm going to say return. I can do this in one line. Dice roll. Die one sides and its modifier. And I haven't actually put in 20s or 12s yet. I think this is beautifully generic. Is less than dice roll of sides, die two sides, and die two modifier. Great. There's a lot of really angry things going on here. Oop. There we go. And what are you complaining about? Undefined name modifier. I didn't spell it correctly. You don't have to spell it correctly. You do have to spell it consistently. In this case, it was both were wrong. I'm going to shrink that a bit. That makes it a little bit bigger for you. That didn't work at all. Oh, everything has gone to pot. Oh, boy. Close. There you go. So, there you go. We have a battle. Now, how many times do we want to run each trial? Well, make it a constant, because I don't actually want to think about that right now. But if I put it in a constant, I can change it easily. And that's what matters to me. Def single trial. And this is number of times. I said how many last time. I think it's actually a fairly compelling argument name here too. And I'm going to say for, I don't really care, in range. That's what I missed last time, of how many. And I'm going to do a battle. And where should I keep these? Well, I think I want to keep it in an array again, a list again. And that is still my results. Though I could just count it right away. Maybe I'll just count it right away. Let's make a docstring so I know for future versions of me what this is returning. Returns a count of how many times the second die wins. Oh, do I have enough information coming in to this function? I don't. So, if battle, and I need to pass in some things. Well, I can just actually take all of these, because I need all of these from somewhere else. And I can slot them in here, because I'm going to get all of this will be passed in. I'm going to pass that to battle. And then count plus equals 1. I guess wins plus equals is equal to 0. I'm going to rename that to wins, because that is better than count, isn't it? Return wins. Def. All right, we have a whole bunch of stuff running here. We're happy with that. Let's actually run it. I haven't actually run it yet. So let's run a single battle just to see what happens. Let's actually run a dice roll first. Dice roll. Roll a d20 plus 2. Oh, that's a 1. Yeah. Aw. I thought it was a natural 20. Do it again. Nope. Cool. I see a 20. That's good. That's a good test. Sometimes we're not always certain that Randint is stupid and doesn't follow the standards. We saw 20 meaning that it does indeed go up to and including the 20, which is important. Let's do minus 100 to make sure our modifier works, which we'd never functionally do. But yeah, that seems to be giving us something. The problem with randomness is you can't predict the result until you have a seed, and then you can. Wins, battle, win. Okay, let's run a single trial, I guess, which will run our battle comparison. We're going to run it twice with a 20 plus 1 and a 12 plus 1. 1. There is 1 win. 0 wins. 0, 0, 0, 0, 1, 1, 1, 1, 1, 1, 1. Cool. Fine. Excellent. So now we've made a whole bunch of single trials, which are still, we are still repeating them. which is good. Now I want to do this a bunch of times. And now what's compelling about this is that I have my trial set up, and I want to run it with +1 and +2 and +3 and +4. That sounds like a for loop. And I can do that for free. I don't have to change any of my existing code. All I have to do is run that a bunch of times. So let's do it. Def many trials are all do experiment. This is really my experiment already. And I don't really need to pass anything to it because I'm going to have a for loop mod in range. I want to go from 0 up to, my hypothesis was that 5 should be a consistent win. So I'm going to go up to 7 to make sure that my modifier can go up to 7. I'll really see that win. And then I'm going to do Meti battles. Right away, I can just print out my results. So this is part of my analysis, is that I can just see my results. Print the D12, and I'm going to start hard coding this. No, I shouldn't. I'm going to put in a placeholder then. Beat plus modifier. Beat the D something this many times. And that is a very clear message. I need a huge format string for that. So my D what? Well, this sounds like a constant to me because I don't want it to change, but I maybe want to change it in the future. So dice 1, die 1 is a 20-sided die. Die 2 is equal to a 12-sided die because that was the science I wanted to do. And I hard-coded this, and that's okay. Because this was a very specific experiment to this. So noddow.format. The D die. Oh, I actually have these switched. I can move this to a 100-sided die too, which is very exciting. Die 1 plus modifier. Mod. I just named it mod here. That's coming out of here. That's from my for loop. Beat the D die 2, which I'm never going to add anything to. Something times. Well, I don't actually have that number yet, so wins times. There we go. I actually have to generate that. Wins is equal to, well, I'm going to do my single trial. How many times am I doing it? Runs. Die 1 and the modifier. And die 2, which is my D20, plus 0. I'm never actually changing that. Though I could put 2 for loops and start changing that one too, and then have a general table based on modifiers. And oh my gosh, that sounds like an assignment. I might do that. That's so gross. I love it. Will this work? Well, not yet. I'm actually going to call do experiment, and my main function ends up being very simple. Do the experiment. I've modeled my experiment. And int is not callable, which is probably true. Line 28. Oh, I don't know how that happened. So plus 0, the beat the D20 a few times. Plus 6, it beat it fewer times. Does that smell right to you? I'm going to have to look at my inputs to make sure that I'm doing this correctly. And I totally know what's happening, because I wrote a docstring. It returned if die 2 beats die 1. So let's swap these back to the way that I had designed it from the beginning. I had switched order in there somewhere, and that's no good. Now die 1 is my D20, die 2 is the one that I'm adding a modifier to. And I'm going to change my output string here. This is where I switched it. Oh, yeah, that's why. I phrased it backwards here. That's interesting. There we go. That looks a little bit more sensible. Are we reliably beating the D20? when we say 500? Well, no, but you can see that it's increasing. Now we can start playing with this. When do we just beat 100 times, or like every single time? We got to add a percentage, and then say wins divided by runs. Yep. And then we can add a percentage. That's times 100 times, and then doop. I make that a 0.2 floating point. And you know I love 0.2 floating points. You can see our percentage increasing. Well, that's nice. We can actually graph this. We can do a lot of things with this. But you can see where it breaks at 50%, which is exactly what we predicted. Going back to our analysis, what was hypothesis 1? Hypothesis 1, it was that it would be about break even at +4, because on average that should work. And then it should be reliable. I don't know if 0.3% over 50% is reliable, but there it is. And that is about what we predicted. And that is something that matters. Science does require that we actually look at the results and compare them to what we predicted. We can't just make no predictions and look at the results and do science. That's not how science works. That is, yeah. You're just looking at the real world. And there's a word for this. It's an anecdote. There's a different word for it. It's not quite science. Whew. 40 lines code. It's not too bad. Super abstract, though. Yeah, keep in mind that that's all of the numbers we slotted in started at line 30 something, which is nice. Okay, how do we represent other things? A deck of cards. Well, do we care about suits? Maybe not. Then it could be an integer. Otherwise, we'd have to make our own object. We can talk about that later. There's also some beautiful math we could do where 1 to 13 are spades, and then 14 to 26 are clubs, and then we could use modulus to find out floor division to see which suit we're in. It's a little bit dirty. I'm not going to make you do that. Don't worry. But it's an interesting thing to model. Compare this data set to a random event searching for patterns. Yeah, we can. This is actually part of AI and machine learning. We're searching for patterns. We actually use randomness to add in lots of meaning and compare it. Well, it's big. It's a big thing. It's cool. Simulate a room by going around a room. Well, mathletes. I'm sorry, I shouldn't call you mathletes. We'll say, well, we have a random room, and then we'll just bounce off the walls. That's easy. But what if your room is shaped like a real room, where you have a closet and there's an alcove, and well, this is an odd shape now. And what we want is full coverage of all of the floor. Well, we can make a program that you could give in any shaped room, and then the Roomba can have a random angle that it reflects, and we can see which random angle would be covering the most of the floor. That is very hard to mathematically model. It's not that hard to simulate. And that's when we can really start adding some nice programming into science. What are the random events? What are the output structures? What are you trying to get out of it? When you're just telling the story, this is what I'm putting in, this is what I'm getting out. There are two different things. Sometimes you can figure it out halfway through the program. Often you should think about it first so you can write your program correctly the first time. Thank you for paying attention. Thank you for programming with me. Thank you for trying this out on your own. Just on your own, without looking back at my code, try to do this. It's kind of fun. Thank you for your time.